Okay, thank you. So welcoming to the stage Håkon, who's going to talk to us about semantic segmentation.
My name is Håkon. I come from the Norwegian University of Life Sciences. And I will be talking about this semantic segmentation of force stands. And that comes from, so my PhD, it was just very broad. It was to use deep learning for force mapping, because we kind of want to build some competence within our group. And then we have this project now, this research center called Smart Forest, which is essentially we're trying to bring new technologies into the forestry sector. So that's kind of how we ended up with this forest stands. We asked the forest sector, can you really need? And this was kind of their pressing need, I guess. So with the conference, I'll just give a short background, what forest stands is, and what the current methods are, and the historical perspective. And then I will say something about the work I've been doing, and then maybe potential for the future work. So first, to define these forest stands. They're essentially like you want to group trees together to make somewhat homogeneous areas. So you have kind of the same diameter of the trees. You have kind of an even distribution of species and more or less the same height and these kinds of things. And you do this because the idea is then the trees could have the same management, and that also you don't want to move a machine just to cut a single tree, so you need to have a larger area for it to make sense economically. And then this has a long-standing history in Norway, so these stands are also used as input data for growth and yield models, and then so we kind of have this system based around this. And there are certain criteria, so we need like a certain minimum, as I said. And historically, this has been done by looking at physical images and then drawing some lines. And then it has improved slightly. So this is kind of the current situations. You have some existing maps maybe, not always. And then you have these special glasses so you can see the image in 3D, so you also get a sense of depth. And then they're essentially starting by the easiest area, so usually clear cuts, water bodies, marshes and stuff, and then filling in the rest as they go. The problem with this is, of course, you have these natural phenomena that kind of change gradually, so you don't always have these crisp, clear lines. So there is some inherent subjectivity in the data. So we have to look at the published data or research, and then one approach is used aerial images, so something like this. Then you can kind of see there are some different textures, there are some different spectral, you can kind of start to make some shapes maybe, but it's a bit difficult. And then you have the problem with shadows, kind of creating some issues in distinguishing even the crisp borders. And then there's this other approach, which is using a canopy height model, which of course it gives also a lot of information, but then it becomes a bit difficult for certain classes. It's like, is this a marsh or a clear cut? Don't know. And then there's this third approach where you're kind of combining both to get both the sense of depth and spectral information. And then most of the research is focused around these region growing algorithms. And they're great in the sense that they do actually make very homogeneous polygons in forest attributes, but then the feedback from the managers is that that's not really what they want. So that's a problem. So we thought, okay, let's do an easy, quick study to start off with. So we just said, okay, from published research, we know that we probably need aerial images and the canopy height model. So we did that. And then we used 1 meter resolution because that's the typical resolution they have for their canopy height models. And then we needed some classes to predict. And then we used an existing map as the reference. And then we essentially said, so we did this division that they usually use, which is related to management. And then we just said that everything else is non-forest, because we don't really care about that currently. So then we asked, okay, do you have a good area for us to start? Then they had this proposal for this large property. And we can see already here there's a slight problem in that we have some time discrepancies in the acquisitions of the different data sources. Yeah, and that's why I excluded some of the images, because there were some clear cuts in the images that would not represent in the canopy height model. And then we had this sort of distribution of the data. And we said, okay, just let's use a very simple model. It's a somewhat intuitive interpretation. And that gives us some, then we can give some feedback to them, and then they can tell us kind of how to guide the process further. And then we got the matrix. And then a problem we found with this matrices is like accuracy or precision and recall and stuff, is that when you look at the map, they can give very different. So even if the, let's say, accuracy is very similar, you can have very like grainy images or very splotchy images and stuff. So we kind of ended up also doing a visual inspection, and then we got something like this. So in this case, it worked very well. We can see there's a good agreement. But then if you look at the top right of the image, we see that there is a problem with the image and canopy height model not matching. And then other times we get something like this. So here the boundaries are quite good, the classification is all wrong. And then if you go and look further into the data, this is because these areas that are falsely classified are very close to the boundary between the classes, which is kind of a problem when you're trying to put these discrete classes on something that is growing continuously. And that also makes, of course, when you're saying if the model is wrong or not, this is maybe less of an important error when you're very close to the boundary as opposed to if you're very far away from it. And then this is another area, and here we can say it's mostly good, but then for this yellow stand in the middle, you can see that the interpreter has kind of dragged the polygon down and to the left, and for me, which is not an expert, that's not very intuitive. It's not very clear to me. And then we asked the people, and they were like, yeah, but the model is probably fine in this area. So you also have, there is some misclassification, but it might not be misclassified. So I think we have shown some promising results, and they're kind of happy with it. But of course, we have these problems on how to kind of evaluate the data, and we also have a very limited data set, so we need to kind of get more data. And then we have this problem with the temporal discrepancy. And then in that case, we have a very good national aerial image acquisition program. So we get both free aerial images and point clouds for forested areas, usually every 5 years. So our idea further is to just try to use that point cloud. It's a bit smoother of an appearance than the airborne laser scanning, but we think it could work well since we're kind of not very interested in very small objects, but kind of have these larger areas. So I think that's all I have to say.
Thank you very much. Do we have any questions in the audience? Okay, I have a question. Yeah. Given that the variability is more at a plot scale, yeah. How do you justify using data at 1 meter resolution? Is that necessary, or do you think you could look at kind of coarser products to, you know, I suppose further expedite processing?
That's also something I've thought about. Of course, there's this amount of information in the data compared to the time it takes to process it and everything. So we were kind of more, so the aerial images, they typically have images of very different resolutions. So 1 meter, then we kind of, okay, then all images kind of can be downsampled to that. And then for the canopy height, that's usually the resolution they use operationally. So we were just like, okay, but if you do it like this, then I can just use it as is. And that also for this national project, also just download it free every 5 or so years. So it will kind of just smoothen the pipeline. But it's definitely something we've thought about. And I guess we haven't made a conclusion yet.
Yeah.
And of course we need to kind of investigate more complex models.
Do you have an understanding of, over which sort of spatial grain amongst those different classes you see the best kind of discrimination of the desired end product? Or
I don't think I quite got that.
I'm just wondering whether you've sort of looked at texture, maybe, is what I'm asking really, and whether there's any information in that. So rather than just focusing on the raw 1 meter data, whether sort of understanding something about, I don't know, texture is an important thing to consider.
Yeah, I think texture is important, of course. I think a lot of these region growing algorithm that has been tested, kind of they're based around this texturing and kind of trying to say something about the variability in texture.
Yeah.
And that's also something we're talking about, like maybe making different modules or like having an ensemble or So we're also kind of trying to just. This was kind of an easy way to just get some result and then see what kind of problems appeared. And then we're currently in the process of then talking to the end user to like, okay, but what do you really want and what do you really need?
Sure.
I think that's kind of also important for us to help guide the further research. Of course, we are kind of constrained in what we are doing by what they want and need, because we could make something that kind of works in our head, but if it isn't what meets their needs, then they won't use it, of course. So it adds some challenge there, I think.
Yeah. Thank you. Any other questions from the audience? Okay, thank you very much.